for this one, that's going to be Q, because remember, groups give you information about the number of outer electrons of a substance. Likewise, the horizontal ones, as opposed to being groups, these are the periods, and so anything in period 3 is going to be on the third row down. Okay, but what we must always remember is that what we appear to be the first row is actually the second row. There is this smaller row of hydrogen and helium on a fully labelled periodic table, but we've got that top row there being period 1, period 2, and then period 3 here, and as you can see there's only L within period 3. Question C though asks us which is a transition element. Transition element is basically the group in the middle. This is the, group, probably the incorrect term there, but this is the block of elements which don't have a group assigned to them. These are just the transition metal elements. They're sandwiched between official group 2 and group 3 here, transitional between metal and non-metal properties and things like that. But M is in that middle block and is one of the transition elements. And the final question on this one is asking us which element has 3 electron shells. This is a throwback to question B, because the period helps to tell us how many shells we actually have. And the number of periods tells us how many shells we have, so the answer is again L. But so as I say, then the period tells you the number of shells, the group helps give you information as to how many outer electrons it has. So for this one, L, the same as for question B. Then go to a more generic periodic table, so without the specificity of certain elements, but asking you about what regions of space and properties of various things we'll have within the periodic table. And the first question is asking us in which region are the non-metallic elements, or the non-metals, found. And the non-metals are found towards the right hand side, which is region 3 over here. And so in order to answer the question, we've got region 1, 2 in both regions 1 and 2, and then in neither region 1 nor 2. So a bit of English really to try and reverse question really. But region 3 is where the non-metal elements are found. And group 1 in the next question, we know that the groups in the previous question, question 4, first vertical column on the left hand side here would be group 1, and so we have region 1 being where group 1 will live. And if we're then looking at the figure of reactions with water, so the types of reactions that we've done with water involve metals, typically group 1, again something in the area of region 1, and we know that the vigor of group 1 reactions gets more vigorous as we go down the periodic table. So we know we've got lithium, obviously we're all the way down to cesium and francium down the bottom. So francium will be a very, very vigorous reaction with water, and so what we've got something there is the bottom left of region 1. Obviously it wouldn't be region 3 anyway, because that's where the non-metals are. They wouldn't react in the same type of way that we've done in year 9 with waters, group 1 metals would do. So bottom left of region 1 is where we are here for the most vigorous. Okay, the least vigorous would have been at the top left of region 1 if we were looking at comparative properties. So question 6, relative masses of subatomic particles. So obviously subatomic particles, we're talking neutrons, protons and electrons, and this is, unfortunately, there's a few areas of chemistry which we just have to learn basically. And relative mass of a neutron is 1, so that will be A. Relative mass of a neutron being the same mass as a proton, essentially. The relative charge of an electron, electrons are negatively charged, and they're given the magnitude of -1. So B, where again protons are oppositely charged, they're positive, and again +1. So that's this next question here. So relative charge of proton. So obviously we're assuming +1 here. So these are all relative numbers. So this can be assigned to relative mass or relative charge. This is a magnitude, a size of charge, and relative. So +1, -1, equal but opposite. So for the proton, it's the opposite of the electron. So A for that one. And then we go into question 7 with a little bit more specificity about a specific element. And in this case, it's carbon and 2 possible isomers of carbon, one of which being carbon 12, the other one being carbon 14. And it's asking us how many protons are in an atom of carbon. So we've got the atomic number, the bottom here, which is 6, and we've got the mass number here, which is 12, and in this one it's 14. Now remember, the bottom number, the atomic number, or the proton number, tells you how many protons you have in an element. For carbon, it's going to be 6. It also tells you, by definition, that in a neutral atom, it's also got the same number of electrons. So if it's got 6 protons, it's also going to have 6 electrons. And we know that when we start organising electrons, we can place 2 electrons into the first shell. So we can't get 6 into one shell, not in the first shell anyway. So we've got to have 2 electrons in the first shell. If we've used up 2 of those electrons, it's going to leave us with 4 left. And the second shell can take 8 electrons. So those 4 electrons which have been left go into that second shell and give us 2, 4. Okay. So if all of the shells had have been 2s, obviously we'd have started to spread them out further and further, but that second shell can actually take 8 in total. So the 4 electrons which are left can quite easily go into there. So we get a 2, 4 structure. Isotopes of a substance then, being though an element with same number of protons, so carbon, got the same number of protons in both isotopes of carbon that were given in this question, but how many neutrons in the carbon-14 version? So as we said, bottom number here tells us the number of protons, also tells us the number of electrons. The number of neutrons is worked out by taking the mass number and subtracting the proton number. So 14 subtract 6 will give you 8. So that will tell you the number of neutrons within the carbon-14. For carbon-12, it would have been 6 neutrons. But for carbon-14, it's 8. So, question 8 then, I'm going to go into a little bit more specificity about some types of bonding in the group 7 halogen compounds. But what we've got in the first instance is a trend question. Remember, elements go into groups depending on reactivity and trends of reactivities and properties. That's how the periodic table started to be developed over time. And this question is asking us about how does the boiling point of the halogens change as you go down the group. So it's worth just trying to remember a few of these. Fluorine is a gas, iodine is a purple solid. So fluorine is going to have a low boiling point because at room temperature it's already a gas. Iodine is a solid, actually sublimes, but it's a solid anyway, so it's going to have a higher boiling point or sublimation point than fluorine would have had its boiling point. And so that trend will be reciprocated down the group. Fluorine is a gas, chlorine is a gas, bromine's a volatile liquid. So we're going down group 7 there, we've got to a liquid. Iodine has gone to a solid, and then as does astatine as well. And coupled with that, as we go down group 7, the reactivity decreases. This is different but opposite to group 1 metals. Remember group 1 metals in the previous question, they increased down the group. For group 7 elements, the reactivity decreases. Fluorine, very, very reactive. Chlorine, lesser. By the time you got down to iodine and astatine, they don't really do a great deal unless you ask them nicely. So reactivity will decrease. So we've got fluorine trying to react with a sodium atom here, and in doing so, you can see by the diagram, sodium's got this one outer electron here. Now it's not going to want this, so it's going to try and give that electron to fluorine. Fluorine has space. Now obviously all the other electrons are paired. This one's not paired up, so it's got a space here for that outer electron from sodium to be given to fluorine. In doing so, metals lose electrons, non-metals gain electrons. That's ionic bonding. Molecular covalent bonding, obviously that will all start to come to fruition if we start to share electrons, and metal and metallic bonding is just when we're looking at metals by themselves. So for this one, donation and receiving of electrons is ionic. So Fluorine, after it's reacted then, will have gained that electron from sodium, and as we've already seen in previous question, electrons are negatively charged. So if fluorine gains an electron which has a negative charge, the fluoride ion will pick up that negative charge. It's only taking one electron, so it'll only get a -1 charge. If it had picked up a second electron, like oxygen would for example, it'd get -2, but fluorine only needs a 1 electron, so it only gets a singular negative charge. In gaining that electron, what it's tried to do is fill up the outer shell. 2 shells. First shell has 2 electrons in it. Second shell had 7 to start with, but obviously it's gained this outer 8th electron here, giving us a 2 electron in the first shell and 8 electron in the ion after it's reacted. And so we've got 2,8 after reaction. This is the key point here. This is after reaction. Starts as 2,7,